Okay, we're going to look at our review packet. Um, the multiple choice of center of mass and momentum. All right, so the first problem here has two different objects like this. So it says a system consists of two objects having masses m1 and m2. Now, what's key here, and remember, as you read the questions, you're looking for key information. So if m2 is greater than m1, that means it's going like this. Okay? And that's important because that's your sign convention. The objects are connected by a massless string hung over a pulley as shown and then released. When the speed of each object is v, the magnitude of the total linear momentum of the system is. So first of all, we know that m2 is greater than m1. So when it's released, m2 is going to go like this, and m1 is going to go up. So when you see the word momentum, because when you're taking the actual exam, the first thing you're going to say is, I know momentum p is equal to mass times velocity. Okay. Then the thing about this is momentum is a vector quantity. So vector quantities have both magnitude and direction. So I have to take the direction into consideration. Okay. So again, with physics, your sign convention is so important. So a lot of times, we use the standard Cartesian sign convention, but we always want to make, let's say, the direction that something's accelerating is positive. So because this is going down and this is going up, we're going to call down positive. All right. So now we know that the total momentum, so the momentum of the first one, m1, p is equal to m1 times v, that's p1, and p2 would be m2 times v. The v is the same. But again, we have to take the direction into consideration. So when we take the direction into consideration, this is negative and this is positive. So the total momentum P is equal to negative m1v plus m2v. And this negative sign came from the direction of m1. But now when I put it all together, because they both have the same velocity, and you look at the choices, you can simplify it and say m2 minus m1 times v is my total momentum. And that's it. So that's choice B. All right, number 2. It says, now this is a classic problem that they always have on the AP test, where like something hits a wall and it bounces off or something like that. So it says this one has two particles. So two particles of equal mass, m naught, moving with equal speeds along the paths inclined at 60 degrees to the x-axis as shown. Inclined, they stick together. Okay? So sticking together is important because they're then going to move off. The velocity of their velocity after the collision has a magnitude. Again, so if I look at the picture here, the momentum of this one is going to be P is equal to m naught v, and this one, this momentum, and remember, since momentum is a vector, it has magnitude and direction. And then this one is going to be P is equal to m naught v. The difference is the directions. Okay? So remember, vectors, momentum is a vector. So you have to take the direction into consideration. So the total momentum before is equal to the total momentum after. So the total momentum before is the one on the top. Plus I also have this one. So these two added together vectorially would add up to the total momentum after. Okay? So now when you're adding vectors, you have to pick a starting point. So here's a starting point. Okay, so it doesn't matter if I do this one first or this one, because I like to have, so let's just start with this one. So this one here, this is where I start. So this is my momentum triangle. This is m naught v naught. Then from the head of this vector, I do the tail of the other, which is this one. So from the head here, I'm going to go like this, and this is going to be m naught v naught. From where I start to where I end up, this is my final momentum, pf, okay? So the question says, the velocity. So I want to find the velocity. So now p is equal to mv. So because p is equal to mv, vf would be p over m. So the total momentum before, okay, is m naught v naught, and then the two masses are stuck together, so it's 2m naught. So when I simplify this, this cancels, so I get v naught over 2. So that was choice B. Some of these questions from a long time ago, I think they're a lot more straightforward now anyway. All right, number 3. So number 3 says, I have this wire thing. So this is a center of mass. So I'm going to do the center of mass of this piece. Then I'm going to do the center of mass of this piece, and I'm going to do the center of mass of this piece. So I would actually calculate it. Some people would try to eyeball it, but it's really hard because some of these are like really close together. So the key to center of mass is you pick a starting point like this. Okay. Now the equation for center of mass, it depends. The general equation is, if I was doing the x, xcm is equal to mx, or I'm going to add them all up over the total mass. Now on the equation sheet, let's see how it's listed on the equation sheet. That's how it looks. XCM is adding up the masses times the distance from whatever your frame of reference is over the total mass. Now a lot of times on the AP exam it's going to be x and y. So then you're going to have YCM is equal to the summation of the mass times the y distance over the total mass. So when we go back to this picture here, let's say we start with this piece here. So this piece here, it says they all have equal masses. So this is m, and this is m. So this one, I can either do the x and the y separate, or I can do it together. So this one is at 0. So the distance from here, from this piece, is just 0. So I have that mass. The x component is 0. The y component would be at the center. So this would be L over 2. Plus, now let's say I do the middle piece. So this middle piece, the mass is m. In the x direction, it's going to be L over 2. And in the y direction, it's 0 because it's on the x. So this is going to be L over 2 times 0. And then the third piece, which is this piece, is again m. The x component, the distance from here to here, is going to be the whole L. And then the y component is going to be L over 2. And if you want, you can do the x's and then the y's and add it all together. And then the bottom of this is going to be m plus m plus m, which is 3m. So when I simplify all this, if I want to simplify the x and the y, m, and m times all the distances, my final answer, because this is 3m in the denominator, is for the x, it's L over 2, and because the 3 m's in the numerator cancel with the 3 m's in the denominator when I add it all up. So it comes out to be L over 2 times L over 3. So then I have to look at this and see where that is. So the best choice is B. And again, usually the ones they have are a lot easier now. So again, if you want, you could do it separate. You can say, okay, let me add up all the x's and say m times 0 plus m times L over 2 plus m times L over 3m. And then I can do the same thing for the y and say m times L over 2 plus m times 0 plus m times L over 2 over 3m. So that would give you your x and y components, which would be this. And then that's how you do that one. All right, let's look at number 4. So number 4, a mass is moving with the speed v towards a stationary mass. The speed of the center of mass is given as, so again, we're doing center of mass. So again, the center of mass of anything is going to be, you add it up, so it's going to be m times that distance. In this case, it's going to be v divided by the total m's, where you add up all the m's. So this one is going to be m times v over the total m. So it says mass m1 is moving with the speed v. So the center of mass is going to be m1v, and it hits a stationary mass m2. So m2, it's stationary, so it's 0. And the total mass is going to be m1 plus m2. So this goes to 0. So it's going to be m1 over times v, m1 plus m2. And if you look at the choices, you pull the v out. So that one is, answer is E. All right, number 5. So this is like a typical problem. So this one, the masses are all the same. Okay. So this is a 4 kilogram mass, has a speed of 6 meters per second on a horizontal frictionless surface. The mass collides head-on elastically, so head-on with an identical one at rest. The second 4 kilogram mass then collides head-on, sticks to a third 4 kilogram mass. The final speed of the 4 kilogram mass. Now, this one is actually a special case. You can calculate them, but what number is this? 5. Again, since M1 and M2 are equal, so you can do it step by step. Sometimes that's why it might this is again a special case that when the masses collide elastically head on, they exchange velocities. Now, I've seen this a couple of times on the AP test, so I think it might help to remember the equations, like v1 prime, and that's going to be the velocity of v1 after collision, is m1 minus m2 over m1 plus m2 times v1. And then v2 prime is equal to 2m1 over m1 plus m2. Again, I don't have these memorized, but I've seen from time, again, a couple of times they've actually asked this, so this would be worth putting in your calculator. So the answer to number 5 is A. And the final speed of the 2 kilogram masses that stick together, number 6. So again, you're doing conservation of momentum. After the collision, the left mass was at rest. So if you did all this, you would find out that v2 prime was 6. And then again, in the second collision, the total momentum before is equal to the total momentum after. So m2 v2 prime is equal to m2 plus m3 times v3 prime. But again, all the masses are equal. So v2 prime is equal to 2v3 prime. And then you just, again, if you do the math, v3 prime, using this, if you substitute it in, you'd have v2 prime divided by 2. So v2 prime would be 6 divided by 2, so it comes out to be 3. A lot of times there's people who memorize stuff, and there's a lot of that. I don't know why on the test. All right, number 7, it says a projectile of mass m1 is fired horizontally from a spring gun that's initially at rest. The combined mass of the gun and the projectile is m2. If the kinetic energy of the projectile is defined as k, the gun will recoil. So again, this one actually, to derive, it's very interesting. So I would put the derivation in the calculator. Again, this is something where you're using conservation of momentum. But if you say, okay, the total momentum before, you have m1, and then you have the velocity of the projectile is equal to m2 minus m1 times the velocity of the gun. If you really do a lot of math, and substitute one equation in the other, you end up with kinetic energy is equal to p squared over 2m. But kinetic energy is 1/2 mv squared. So all right. Number 8 is again one with center of mass. And again, what you're going to do is you're going to take each piece. So you're going to pick a starting point. I always do the lower left, and they even put like origin. So you're going to do 1, 2, 3, 4. So for each piece, you're going to do the x and the y to that coordinate, just like this one, but now it has like a little top piece. So if you want to do the x separate, the x is going to be, so if you start with this piece, this is the x part is 2 times 0. Then if we do this piece, you're going to do again 2 times 1. Then the next one is 2 times 2. And then the top one is it's half. So if this is 2m, 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 this mass is only half. So this is just going to be m. And then the distance of the center of this from here to here is 1.5. So that's the part that's tricky. All over the total mass, which is 2 plus 2 plus 2 plus m. So when you do all this, you get 15 fourths m. And then you do the same thing. What number is this? 8? I'm going to rework number 7 a different way. Besides curving coming in, I'm going to... and then the y center of mass, now I do the same thing for the y. So 2, this mass is 2, times the distance from the center of the y here would be 1, plus this mass is 2, times the distance to the y is 0 because it's on this axis, plus this one is 2, times 1, because from the center to here is 1. And then the last mass, this is m, times the distance from here to here, which is 2. And then you add up all the masses on the bottom again, which is 2, 4, 6, 7. So when you add up this one, you get 6, 7. So then that's going to give you the x and the y coordinate. Some people do by looking. I always calculate the center of mass. All right, number 9. 2 balls are on a frictionless horizontal table. Ball X initially moves 10 meters per second, so that's the initial velocity. So here it is. As shown, it collides elastically with an identical ball Y, so they have the same mass. So that's what this identical is important, because that means they have the same mass, which is initially at rest. After the collision, ball X moves off 6 meters along 53 degrees. Which of the following diagrams best represent the motion of Y? So again, vectors are added, head to tail, momentum is a vector quantity. So I would just do this pretty much, so the total momentum before of the system is just the momentum. Remember, the total momentum before is equal to the total momentum after, but vectorially. So the total momentum before is just going to be the momentum of ball X. So if I drew that, here's the total momentum before. This is px, and it's going to be mv, and it's going to be whatever the mass is. They don't tell us the mass, do they? No, they're identical, times 10. So whatever it is. So this one's going to be 10. Now the other two, so it's 10 times whatever the mass is. So the other two have to be, so basically you have this one going along and it hits the other one. After the collision, they're going to end up like this. So this is where I start. This is after the collision. This is ball X goes off this way at 53 degrees. And it's going to be m times 6, or 6m. From the head of this vector, I draw the tail of the other, because these two added up head to tail have to equal this. All right. So then this one is the one that I need to find. So how do I find this? Well, this is a right triangle, and this angle here is 37 degrees. So to find the magnitude of it, this squared, this plus this squared is equal to that. So I would say that, so this is going to be ball Y, but I don't know, again, but they're the same, so it doesn't matter. So Y is equal to this, 10 squared minus 6 squared. So that comes out to be the square root of 64, which is 8. So remember, this plus this vectorially equals that. So this is just knowing that vectors are, momentum is a vector quantity. All right, so now it says a balloon of mass m is floating motionless in the air. A person of mass less than m is on a rope. The person begins to climb up relative to it. How does the balloon move relative to the ground? So this is kind of like a center of mass problem. You're not really doing a calculation. You know, you're just kind of thinking about it conceptually. So because the center of mass remains stationary, so it says, how does the balloon move relative to the ground? Okay. So again, this again is, the questions now are not going to be like this. They're going to have like a picture. This one has a lot of verbiage in it. It might help to conceptually draw a picture and say, okay, here's the balloon M, and there's a person with less than M on the ladder hanging from the balloon. So you just know that little m is less. So again, he's trying to climb up the ladder at Unisport, so he's going this way. Okay. So how does the balloon move? So again, initially, here's big M and little m. So the center of mass, you know, let's say the center of mass of the system is here, okay, closer to big M, because this is little m. So because there's more mass here and less mass here, the center of mass would be closer. But now he starts to climb up the ladder. So it says the person begins to climb the ladder at a uniform speed relative to the ground. How does the balloon move relative to the ground? So again, this is kind of confusing in a lot of sense. So if you want the center mass to be in the same place, like I said, you have to think about the forces and think about it as a system. So the center of mass must remain stationary. So the smaller mass this little guy, he's moving in one direction, so the larger mass compensates by moving in that direction. So this one definitely is tough to conceptualize. I'm curious how many people missed that one. All right, number 11. If one knows only the constant force acting on an object during the time which it acts, one can determine. So you have the force. And then it says you know the time. Well, this is the equation, Ft is equal to impulse. So this is basically just knowing the definition that impulse is equal to Ft. Now remember, that's also equal to m delta v, which is a change in momentum. So this is just a different weird way of asking what the definition of momentum is. That's all that is. So that should be like a first pass question. Some of these are kind of weird. All right, number 12, it says an object of mass m is moving with the speed v naught to the right on the horizontal. So here's the picture. When it explodes into two pieces, subsequently one piece of 2m moves with the speed v naught to the left. The speed of the other piece is. So again, the key here is the total momentum before is equal to the total momentum after. So the total momentum before is just this little box, which the total momentum before is mv naught. Now it's going to split in pieces. Okay, so after you're going to have, let's say the pieces are m1 and m2. So this is the total m, and total m is equal to m1 plus m2. So then after you're going to have m1, and then it's going to have some velocity plus another piece which is going to have a different velocity. And I use prime to do after the collision because I don't like to do double subscripts. So you have mv naught is equal to, so if you read it, you have to be careful. It explodes into two pieces. One piece of mass 2/5, so this one, which is 2/5 m, that's what m1 is, moves with the speed v naught over 2 to the left. So this speed is v naught over 2, and it going to the left, so I have to establish my sign convention. Well, if it's initially moving to the right, and this is positive, this is going to be negative. Plus m2, so what's the speed of the other piece? So the other piece, well, now I'm going to use common sense. If this is m, and this is 2/5 m, this has to be 3/5 m. So that might be something that people forgot. So 3/5 m times v2 prime. So now after this, it just becomes an exercise in like algebra. So this is the velocity I want to find. So I would just, multiply this out, mv naught, and then 5 over 2. So then you would end up, basically doing stuff with fractions. And after you do that, you just rearrange it and solve for this v2 prime. So minus, well, these 2's are going to cancel. So this is going to be v naught, mv naught over 5 plus, I want to get rid of this one by itself, 3/5 m v2 prime. So what I want to do is I want to get the v on one side by itself, and I want to get rid of all the m's. So first I'll move this over, so I'll have m v naught plus m v naught over 5 is equal to 3/5 m v2 prime. I want to get rid of the 5, so multiply. From here it's just algebra, so whatever way you want to do the algebra, you just want to solve for the v2 prime, and that you can do by yourself. So anyway, it comes out to be, when you cancel the m's, because you're going to end up canceling the m's, you could cancel the m's now actually, and so you would get v naught plus V naught over 5 is equal to 3/5 V2 prime. So if I added this together, 1 plus 1/5 is 6/5. So 6/5 V naught is equal to 3/5 V2 prime. And then you just continue to do this and solve for V2 prime. So you can then divide by that and get that V2 prime ends up being 2 V naught. Well, this is obvious because they both have 5 in the denominator, so you could just cancel that. I don't know why I didn't see that. Oh well. Alright. Why is this not coming out good? Alright, there we go. Alright. So, number 13. Alright, so this is like a different one we did. So it says a 5 kilogram sphere is connected to a 10. This is on a rotation one. It's the same problem. Which of the 5 letter points represent the center of mass? So remember, if I want to do the center of mass, this is 10 and this is 5. Now if you wanted to calculate it, you could use the equation. X center of mass, this is going to be my frame of reference. 10 times 0 plus 5 times this whole distance. I don't know what I would call the distance. Let's say L over 10 plus 5. L is the whole length. So you have 0 plus 5L over 15. So then this reduces to L over 3. So basically from here, the center of mass is going to be 1/3 over. So then you look at the picture and say, which one looks about 1/3? And that's why the answer is B. All right, number 14. It says the graph shows a force on an object of mass m as a function of time for the time interval 0 to 4. The total change in momentum of the object is. So remember, the change in momentum is the impulse, which is the area under the curve. So what's the physics you have to know here? You have to know on a F versus T graph, the impulse is equal to the area under the curve. Now, besides that,
teachers, this.
So, and remember, impulse is also equal to delta P, which is m delta V. So it says from 0 to 4, what is the total change in momentum? So I'm going to look at the graph and do the areas. So here, this is a rectangle. So the area of a rectangle is base times height. So 2 times 10 is 20. So this is 20. Okay. Then, and again, this is positive 20. Then here it's going to be negative 20. So when I add the areas together, the area is the change in momentum. So the answer is 0. All right, number 15. So here's another picture. So it says, as shown in the top view, a disk of mass m is moving horizontally to the right with a speed v on a table with negligible friction when it collides with the second disk of mass 2m. So first of all, the momentum of this one is m times v. The momentum of this one is 2m times v over 2. The two disks stick together upon impact. The speed of the composite body after the collision is, so this is just, okay, so I have mv plus 2m times v over 2. They're going to have combined mass, so it's going to be m plus 2m, and then my combined velocity is going to be v prime. So then I just do algebra and solve for that. Okay. We could do that in regular physics. All right. Number 16. It says 2 people are initially standing on a frictionless ice. They push together. So one person is 100, moves to the left. So you have the mass which is 120 going to the left. So if I'm saying left, I'd say -2. Well, the other person moves to the right, so you have to make this. What is the velocity of their center of mass? So again, this is kind of like a recoil problem. So this is just recoil. So initially they're both 0. So they, 120 times 2 is 240, and 80 times 3 is 240. So it's equal and opposite. So initially it's 0. Kind of stupid, but that's the way the question is. All right, number 17. An object having an initial momentum may be represented by the vector above. So this is the total the initial momentum. It strikes an object that's initially at rest. Which of the following sets of vectors may represent the momentum of the two? So this is if the other one's at rest, this is the total momentum. So the total momentum before is equal to the total momentum after. So again, here's my original. And this is the total before. So the total before has to be the total after. So I have to look at the other two and say, well, which two vectors added together head to tail equals this? So, choice A, you add these together head to tail, it's 0. You add these together head to tail, it's one long thing. You add these head to tail, so from the head of this one I do the tail of the other, that's the result, and that's wrong. So when you look at these other choices, again, if this is where I start and this is where I end up, I need vectors that look like that head to tail. Now what made this tricky is instead of showing them like this, they show them tail to tail. So I have to have one like this, and I have to have one like this to add up to this. So the answer to number 17 is E. And again, sorry, it has to do with adding vectors head to tail. All right, let's look at 18. So 18, a 2-kilogram ball collides on the floor. They love this problem. They have this problem like it's a wall, it's a floor, and it just has to know with adding vectors vectorially. So at an angle theta and rebounds at the same angle, which of the following vectors represents the impulse? So the first thing you're going to do is you're just going to say impulse is equal to the change in momentum. So this is equal to m delta v. And delta v is equal to vf minus v naught. So that's basically the key to this problem. What is this 18 even asking? So if you look at the two, when the ball hits, here's my initial one, right? So the components of this one is going to be, this is the y component and this is the x. Here's the other vector, okay? This is the x and this is the y. So you see here these x's are the same, but these y's are equal and opposite, okay? So when you look at this, the impulse is going to be the change in momentum. So 18, the answer is E. Number 19. This is the calculus. So the momentum of an object as a function of time is given by the equation. So if you see anything like this, it's calculus. So what do you need to remember here? You need to remember that F is equal to dP over dt. So it's just calculus. So you just take the derivative of that, which is an easy derivative. So you just, this is like a really simple, the calculus ones are usually easy. All right, number 20. What is the total kinetic? Oh, so this has two problems. So the two things hit like this. The 1 kilogram puck is moving directly east. And this one's moving north. Okay. So it says, what is the total kinetic energy of the two-puck system before the collision? Okay. So the kinetic, remember, kinetic energy is scalar, so kinetic energy is 1/2 mv squared. So I just do 1/2 mv squared for each object and I add them up. Number 21, the total momentum. So again, they deliberately make this, momentum is mass times velocity. So this one here is going to go like this. So 2 times 1.5 is 3. This one, 4 times 1 is 4. So this is 3, this is 4, from where I start to where I end up. So these two added head to tail is going to give me my final momentum. Well, it's deliberately a 3, 4, 5 triangle because this was written back when you couldn't use a calculator to do the multiple choice. All right, the boat. So it says, as shown, two students are on opposite ends at rest. The student in the front throws the heavy ball to the student in the back. What is the motion of the boat at the time immediately after the ball is thrown and later after the ball is caught? So after the ball is tossed, again, think about, this is kind of like recoil. So